Zoom, I guess you can jump up and down and wave your hands and I'll be able to respond to your questions or something, but feel free to interrupt me. I'm going to turn on my screen right now. And let's see, where do we go here? Right here.
You got it, man.
Okay.
Looky there.
Oh, look at that.
Is that working now?
Yep.
You're there.
Well, we're going to get talking about radio signals and fundamentals tonight. And the very first thing we're going to do is talk about radio waves. But before we talk about radio waves, I'd like to talk about something a little bit more familiar. Let's think about waves in your favorite lake. And you can think of either throwing a rock in the lake and seeing the circular waves come out from it, or you can think about a boat going by and rocking the dock and the other boats that are in the area. But I'd like you to think of those waves in the water, two different waves. First of all, think of them as taking a snapshot with the camera. And with a snapshot, you can see several waves together and you can see how big they are and you can see how far apart they are. And then think about those waves in a different way. Think about them as a video clip. In other words, you can see the waves moving and now your eyes will focus on a couple of them and you can see which way they're going and you can see how fast they're moving. Well, we're going to talk about electromagnetic radio waves now. And first of all, since there's two parts of the word electromagnetic, let's talk about the electro part of it. If we have two pieces of metal that we have separated by some distance and we have a voltage that's energizing by a battery across these plates, then between the plates, we will have something called an electric field. And depending on the polarity of the battery, you can have a field that is directed in one direction or the other. You can see on this slide that it's headed downwards. But if you have a different kind of a voltage source that varies back and forth between plus and minus, which is what an AC voltage does, then you can think of that electric field changing directions every time the sine wave goes by. So you can either have a static electric field or you can have a moving electric field like this slide shows. Next, we can do the same thing with a coil of wire generating a magnetic field. Now, there's no separation of plates here. Just imagine a coil of wire. The coils of wire are going around and around like this throughout this cylinder, and then we can have a DC voltage energizing that coil, and that will result in a magnetic field that goes in one direction. And if you go around, the current goes around in the direction that I'm doing with my cursor right now, the field will go up, showing this arrow right here. Or you can have you can have a alternating current voltage energizing that magnet, and then you will have the field, the magnetic field, changing direction back and forth. For one part of the cycle, it'll be oriented upwards, and the other part of the cycle, it'll be oriented downwards. So now we're going to try to put those two words and those two concepts together. This is the snapshot view of the electromagnetic wave. The snapshot shows, just like in a water wave, that we've got some hills and valleys. And if you look real carefully, the ones that have stripes on them are considered to be the electric wave, the electric part of the field. And if you look at the gray parts, that's the magnetic part. And notice that they are locked together. That's one of the miracles of electromagnetic waves. They are totally locked together. The peaks of the electric field and the peaks of the magnetic field occur at the same time. And now I'll take that other image of the waves in the water and think of this thing as a moving field. And you can think of this whole thing that we're looking at right now as an arrow being shot at high speed through the air. So this whole thing that we're looking at is moving like crazy through the air. And that is what, about as close as we can get to describing what an electromagnetic wave looks like. Actually, you can't see it at all, but you can think of this as being a water wave that's just moving very fast. In fact, it's moving so fast, it's moving at the speed of light. So in order to talk about these waves, we need to use a few new words. Well, first of all, how big are the waves? We can see that this amplitude over here means how big the wave is. Now, there's a couple different ways you can describe the amplitude. There's the distance from the middle point to the top. That's one way of measuring amplitude. And then there's another way of measuring it, and that's from the top all the way down to the valley, the bottom of the thing. So you could measure it that way. And then there's a more sophisticated way in addition to that we use quite a bit too. The frequency, which used to be called cycles per second in the old days, is how many times this thing is changing per second. How many times how many of these we get per second. And with radio waves, there's quite a few. The period is how far apart they occur in time. Now remember, this is going through the air, shot like an arrow, and the amount of time it takes for this part of the wave to get to this part of the wave, that's called the period, and it's measured in seconds. Oh, I forgot to mention that they changed the units for frequency a long time ago, and now they call it hertz. So that's the substitute for the old cycles per second. And then it is also possible that a radio electromagnetic wave can have more than one frequency in it at the same time. You won't have a wave that looks as pretty as this sine wave right here. If you have several frequencies, then we call the lowest frequency the fundamental. And if there is a frequency that is 2 times that, then we call that frequency the second harmonic. And if we have a frequency that's 3 times the fundamental, then it's called the third harmonic. Notice that with this language right here, there is no such thing as a first harmonic. We go right from the fundamental to the second harmonic. Any questions about that yet? Okay, now we're going to do something more, the wavelength. And that's how far the radio wave travels during one cycle of the fields. So wavelength, you can see this guy walking. If you think of it as a wave in the lake, that's how far apart the waves are. You can either think of it from the tops of the wave to the other top of the wave, or you can think of it as the valley to another valley. We give the symbol lambda, a Greek symbol for the wavelength. And we've already discussed the fact that these waves are traveling at the speed of light. And so now that results in a way to refer to an individual wave 2 different ways. You can talk about waves by their frequency, for example, 50 megahertz, or you can talk about the same wave by their wavelength. Lambda equals 6 meters. Now, since they travel at the speed of light, there is this really neat little formula that you as a beginner will use just about every time you think about frequency or wavelength, and that is that there is a very good, easy relationship between them. And that's lambda equals 300, the number 300, divided by the frequency, but now we use the frequency in megahertz. So for example, in this case over here, if we have lambda and frequency, you can see that 6 equals 300 divided by 50, or you can think of 50 equals 300 divided by 6. You can do it either way. You can say F equals 300 divided by lambda, or you can say lambda equals 300 divided by F. And when you get started, you do that all the time because frequency can go up, frequency can go down, wavelength can go up, and wavelength can go down. Now let's talk about different parts of the electromagnetic spectrum. It has been divided into ranges where each set of waves in that range behaves slightly similarly to waves in that range. So we have names for these different ranges or segments of the electromagnetic spectrum. Certain parts of that spectrum are used for communication, and they're called radio waves. There's always other kinds of radio waves too. There's light, for example, there's X-rays, there's all kinds of different parts of the spectrum. Here we have a slide that shows the different parts of the spectrum that you'll ever be aware of. Well, most physicists go farther than this set of ranges here. But we have very low frequencies, we have low frequencies, medium frequencies, high frequencies, very high frequencies, ultra high frequencies, super high frequencies, and extremely high frequencies. Most of the time when you're doing work with radio, we're going to be talking about this group right in here. Right in here. This is the part of the spectrum that we like to work in the most. Now, each one of these ranges right here has certain specific limits in frequency. That's what these are shown as, limits between frequency. This is a factor of 10 higher frequency right at this point than the frequency at this point. So we say that the high frequency band extends from 3 megahertz to 30 megahertz. If we want to do the reverse thinking where we think in terms of bandwidth instead of, if we think in terms of wavelength instead of frequency, then that would be 100 meters to 10 meters. So we work down here. When you first get your first handheld radio, you'll probably get one that works in this range right here at 144 megahertz. And if we divide 144 into 300, we get about 2. So that's the 2 meter band. So you'll be spending some time here, and then when you get a little bit fancier radios, we'll be spending a little bit of time here. Now, the part of the band that you've listened to when you were a kid is down here, the AM radio band. That's down around medium frequencies because the range of frequencies there starts at about 500 kilohertz and goes to 1700 kilohertz. Okay, so these are the different bands in the electromagnetic spectrum. Okay, we talked about these. They're bands. We talk about the AM band, or the citizens band, the CB band. And typically the signals that are within these bands are usually of the same type. Now ham radio guys like you and me, we're going to have a lot of different kinds of signals, and we have a lot of different types of signals, and we're going to have more parts of the band than just our AM radios and our FM radios used to have. Okay, so now this slide shows one part of the band. It shows an example of signals in the AM or medium frequency band. It shows, for example, in a small town, there might be 4 different radio stations, and this might be what the spectrum looks like within that band for that town. For example, there's a radio station at 570 kilohertz. There's a radio station at 800 kilohertz. There's one at 1,000 kilohertz, and there's one at 1,310 kilohertz. Now, these signals are electromagnetic waves that are coming at us from all different antennas, and they're in the air all the time, all together. And if we want to listen to a radio station, what we do is we do something called tune. We're tuning in a signal by having our radio receptive to one particular band. And hopefully our radio will reject the frequencies that are in another band. So for example, if we want to listen to this, we tune our radio until it says 1,000 kilohertz. And the closer we get to 1,000 kilohertz, the more we can hear in that radio signal. Any questions about that? Notice down here that we can talk about these signals in terms of kilohertz. And if we wanted to talk about that in terms of megahertz, then it would be 1 megahertz, because that's the relationship between kilohertz and megahertz. Okay, how do electromagnetic waves affect us? Well, if we are putting a signal, an electrical signal, and the electrical signal doesn't have the word magnet on it, if we put an electrical signal into an antenna, then the moving electrons in that electrical signal, they correspond with the miracle of electromagnetic waves. And what happens is that an electromagnetic wave will be emitted from the antenna. So the fact that the electrons are moving causes a little bit of magnetism on their own, and that combines with the miracle of electromagnetic waves into creating that wave that is emitted from the antenna. So we can take a signal from a transmitter, make the electrons move, and we make the energy change from an electrical signal into an electromagnetic wave.
Ron,
Yes.
so that antenna is picking up all those frequencies that are being broadcast.
Well, right now, this slide focuses on the transmission part. So if we put
Okay.
a signal into an antenna, we're going to generate an electromagnetic wave for that particular signal.
Gotcha.
And yes, the very next slide, which you guessed, Bruce, is going to talk about the other way around. The same process works backwards. So if we have an electromagnetic wave in space encountering an antenna, then it makes the electrons move in that antenna in sync with the wave. And yes, if there's several stations in that area, if there's several stations emitting at the same time, and there always is, then the antenna itself will pick up all those signals and they'll make the electrons move. And so there's a lot of different things going on with these little bitty electrons. Fortunately, there are very many electrons that are moving in all different directions in the antenna. And then we're going to pass that antenna energy into our radio. And that's where the selection process starts. So we can transfer electromagnetic energy into the antenna and make electrons move. And then these moving electrons will go into our radio receiver, and we will do something called detect them. And that involves focusing on just one of those radio signals that are in the antenna all at the same time. Does that help, Bruce?
Yep.
Okay, now here is an example of what the ARRL sends us in order to learn all these details. And I have to admit that when you're beginning, there's too many details to learn all at once here.
Pretty busy.
So let's just focus on some of the things that you can see that understand. Probably, like I said, the first thing you'll do is you'll get a handheld radio, and you'll be using that radio on the 2-meter band, which happens to have a frequency of 144 megahertz, anywhere from 144 to 148. So the limits of the 2-meter band that we are authorized to use, and this is something that's promulgated by our government and by the fact that we have certain parts of the spectrum, but not all parts of the spectrum, is that if we tune our radios to 144 megahertz or more up to 148 megahertz, then we can transmit and receive on that band with our handheld radio. I say that because it's probably the easiest thing to get started with. And notice that there's a T over here, and these initials, they correspond to different license levels within the ARRL and within the FCC that regulates all this stuff. The T there stands for the technician level, which is what you're trying to get from this course and to pass that license exam. So right now, this club has a frequency of 147.06, which is right about in there somewhere. And we transmit and receive on that radio frequency all the time when we're talking to each other within the club. Other clubs have different frequencies. They might have one down here. As we get more experience, technicians like to get over into other bands, and here's a 6-meter band. You'll probably see this one pretty soon in your life if you get into this licensed stuff. And then there's a lot of other bands, and I won't really talk about a lot of them, except they start over here with real long wavelengths over here, and they keep getting shorter and higher frequencies by going down this list like this, and we finally get over here to where there's a set of bands available at very high frequencies, 1,240 megahertz or 1.24 gigahertz. And that's up pretty high frequencies, but we are allowed to send signals even if you're at the technician level because of this T that's right there. And there's actually higher frequencies than that. Here's signals down here at 5.925 gigahertz that are possible, and there are a lot of even higher frequencies. Now, we don't ordinarily spend a lot of time as technicians in this level, but it is a place to go when you want to get sophisticated and do a lot of other things. And the rules of what frequency is the lower limit and what frequency is the higher limit is one of the more complicated things that we have to get started with and eventually learn several of these in order to pass the license exam. But you don't have to learn them all at once. I mean, they might want you to learn all at once, but it's very difficult to do that. Just keep in mind that the T's are where you want to focus. The T's, see, there's a T, there's a T. There's a T down here, but look, it's very restricted. And you won't find very many T's as you get into the longer wavelengths. And what is the reason for that? The reason for that is that these signals in the lower wavelengths, they go a long ways. It's amazing how far some of these low frequency bands will allow you to transmit. In other words, these are the bands that allow you to go around the world with your radio. These bands over here, the 6-meter and the 2-meter, they're more local. You don't go around the world with these things unless you've got some super equipment. There are some exceptions. 6 meters once in a while it performs miracles due to different things in the atmosphere, and 6 meters can sometimes go a long way. But the fact that they go shorter distances allows the FCC to allow technician level licensees to get onto these bands and to fool around and to talk to their friends. Okay, any questions about that? I know that there's a lot of information there, but we won't talk about all of them. Okay, moving on. We're going to look at some of the questions that you might see on your exam that relate to this material that we've been working on here tonight. First of all, what is the name for the distance a radio wave travels during one complete cycle? And I like to call on folks, but I don't see too many folks over here and the ability of this Zoom session to work and help me identify you all. So I don't know if anybody wants to shout out what's the answer to this question. You might try it.
How about C?
See?
C, that works. If I
C.
click the screen again, you'll see that that is the right answer.
Woo, 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 got one.
Very good, Sharon. Okay, let's do another one. How fast does a radio wave travel through free space?
Speed of light. A.
Okay.
Speed of light, that is correct.
Woo! 2 to 2.
See, you're almost passed already.
Are we on the
You're
turnpike?
ready
These are
to
the real
test.
questions that you'll see on the exam. I don't know if you'll get this question, but these are we're going through some of the questions that they could put on your exam.
Well, I just hope they give me the easier one, okay, guys?
Yeah, you get some easy ones, and there'll probably be a couple hard ones. You don't have to have them all right, though. You gotta, you know.
Oh, I guarantee you, Ron, I'll miss, you know, something.
Well,
Don't bet on it.
Up to 9.
just be optimistic and let's go through some of these other things, you know, and ask questions if you like. I can try to explain them the best I can. Okay, here's another one. How does the wavelength of a radio wave relate to its frequency? This one requires a little more thought. By the way, it's all multiple choice, so you get to choose one of these. You don't have to come up with your own answer.
We think it's B.
I think it's B too.
I think you're right. Let's
Woo, woo. Go girl.
Wow, there's another hard one down this time. You got a hard one. Okay, what's the formula for converting frequency to approximate wavelength in meters? Now you have to remember some details here.
Oh, I wrote this down. Okay, so it is the lambda, right? And then C over F. So I missed what C over F is frequency. So 300 is the constant. So 300 divided by frequency.
Yep. D.
300 divided by frequency gives us wavelength. So
You
which
got it, Cody.
Go
Yes.
girl.
Wavelength is in hertz divided by 300. B. Okay,
It's
so it's B. C.
See.
Okay.
Wait a minute, we got different, I hear people say.
I think it's D.
D for David.
One of the things you do have to
D.
remember for this formula
Oh, it
is
is.
the frequencies
It
that
is.
we're working with are in megahertz, not in hertz. We're dealing with megahertz.
D.
D is in dog.
Come on. There it is. Did she score her first goal?
Yes.
Hey, you guys, my kid just scored her very first own soccer goal.
All right.
Congrats.
Are we all okay with this?
The
This
great
is
equalizer.
what you have to learn.
Yeah. Definitely, since I just messed that question.
Okay. Okay, let's go onwards and upwards.
I even
What
saw
property of radio waves is often used to identify different frequency bands?
I'm
A
A.
for sure.
A. A.
A.
Hey.
I hear 2 A's. I think you're right, guys. There's another one for you, the group.
See what wine will do for you?
What'd you say, miss?
See what wine will do with you, a glass of wine?
Probably a good bottle of wine would be a good help to get through the license exam.
They may not let you take wine to the
Oh, I
test.
know that, but it might be a good thing for you, Sharon. Okay, what are the frequency limits of the VHF spectrum? Now, this is not the limits of one particular band that we looked at in that color chart. This is the definition of the limits of the
Very and
VHF
ultra.
part of the entire electromagnetic spectrum.
Oh, man.
Is it B? It's 30 to 300 to
Yeah.
30.
In order to answer this question, remember that I said that you'll probably be spending a lot of time on the 2-meter band, which is at 144 megahertz, which is right in the middle of the VHF.
I'm changing it to B.
B is the right answer.
Woohoo!
There you go.
I'm getting more wine.
I'm glad we got some good spirits going tonight. Okay.
What is the name of that spirit you're
limits
drinking?
of the UHF spectrum? Now, we're not going to spend as much time up here as before, but since you can kind of remember that UHF is right above the VHF, that might help you answer this question.
Would it be
D.
D?
D.
Oh, I hear some different answers this time.
D is in dog.
Delta.
Yeah, D is in dog.
D is in dog, and that is the right answer. Notice there's a one here that throws you off a little bit. You got to
Yeah.
remember that it's megahertz that we're talking about and not kilohertz, or else this answer here might throw you.
Right.
Okay. What frequency range is referred to as HF?
C.
C.
D.
C.
C.
I think I heard some wrong answers. I'm not sure.
It's 3.
Let's see. Is
Not
any-
on our frequency.
Yeah, we got C. We got cookie. It's number C.
Okay, 3 to 30 megahertz.
Well, we did.
That's just below the 30 to 300, right? A lot of threes. There are threes in this group of
Mhm.
bands. We got to remember the threes. But once you get to remember VHF, and that's 30 to 300, then you can kind of scoot all the rest of them one way or the other. What is the approximate velocity of a radio wave as it travels through free space?
B.
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 B is in boy.
Bravo.
B is in bacon.
B as in bacon.
Yep.
She's got breakfast on her mind. And that's right. 300 million meters per second. This one here might throw you, but that's supposed to be miles per second, not miles per hour, or that would have been close too. Everybody okay with that? What's the unit of frequency? It's not cycles per second.
Hertz.
A. Hertz.
Hertz.
That's right, Hertz. In honor of Mr. Hertz, a famous guy.
Bankrupt.
The car rental guy.
Yeah.
Our rental guy, yeah. Okay, what does abbreviation RF mean?
Alpha.
A.
A. Alpha.
I think we're right there. Yep, there it is. You almost passed your exam. Okay, that's a little bit of a question session for the topics that we have had up till now. Now we're going to go on with some more stuff. And this part is called modulation and bandwidth. So we're going to talk about 2 new words here and how radios use these words to go back and forth between signals leaving the radio, going to an antenna, and signals entering the antenna and coming to the radio. First of all, let's talk about what a radio kind of looks like in a very, very rough black box type of way. There are a couple different parts to the radio. First of all, there's a transmitter and there's a receiver. But notice that there's only one antenna. Now, obviously, it doesn't take long to think about this, but if your transmitter, which is putting out lots of power, puts that energy right into the receiver, it's going to blow the receiver to bits. So there's got to be something that stops that from happening. That's called the transmit and receive switch. This switch allows one of these boxes right here, either the transmitter or the receiver, to be connected to the antenna at one time, but not the other one. So this switch has got to work. This switch has got to say, okay, transmitter, it's your time, or receiver, it's your time. Because the signals that are coming into your antenna from other radios, they're nowhere near as strong as the signals that you're emitting from your transmitter. Now, in between this switch and your antenna, there's actually two parts. There's the feed line that's more or less a coax cable that goes to the antenna, and then there's the antenna itself. So there's a lot of different stuff we're going to learn about. Maybe not tonight, but if you get into ham radio, you need to understand how these feed lines are put together and how these antennas look and where they should be put and how they work and all that. Together, all this part right here, not including the antenna, is called the big word transceiver. That just combines the two words together in a nice, convenient way. So when you go out and buy a ham radio, what you're doing is you're buying a transceiver. Then we have to buy another gadget called the power supply, and that allows these two things to work. And that power supply is usually based off of 120 volts in your house, and it transmits power to the transmitter, it transmits power to the receiver. Okay, now what happens when we have a radio communicating? Well, if we're transmitting, then we're taking information, either your voice or data in the form of a computer program or TV or commands to a military installation or something like that. And we convert that to electronic form. We convert that to the electrons that are moving back and forth in the circuits in the radio. Well, this information that's in electronic form is added to a radio wave. So we start, the radio is capable of making a radio wave, and the radio is also capable, the transmitter is also capable of taking the information that we want to send and adding that to the radio wave. The radio wave then carries that information from the antenna into space. Okay, during reception, the radio wave that's carrying this information, actually all kinds of radio waves that are out in space are intercepted by the receiving station's antenna. Now this is where the receiver does a fairly big job, and that is that they extract the information from that received wave. And not only do they have to get the information out of that particular radio wave, but they got to distinguish the radio waves that you want from the other radio waves that are entering your atmosphere and your space at the same time. So the receiver does a nice big job. After it gets that information, it's presented to you in a format that can be understood. For example, the speakers, or a TV picture, or words on your screen. Okay, now let's talk about this a little bit. Adding and extracting. Adding is the transmitter's job. Extracting is the receiver's job. Well, that can be an easy job or it can be a fairly complicated job. Okay, so this is part of the interest in ham radio because we're going to learn about how these things work. We won't learn them all tonight, and you won't learn them all tomorrow night, but there's a lot to learn, and it's interesting if you get into it.
I do
And
have
so-
a question real quick.
Go ahead.
On some of the more complicated ones, is there a checksum or something that your TR would send back saying they received the communication?
Not an analog ham radio, but there definitely is when you get into digital ham radio.
Ah.
Analog ham radio is very similar to listening to your car radio, okay? And yes, there are some digital radio stations out there, and you can get into digital radio stations with ham radio, but the first kind of level that you get to is holding that handheld radio in your hand. It's something that's about as big as a carton of cigarettes, or maybe even much smaller than that. And that will be no checksums, no digital stuff going on except for what's inside the radio. Now, I've got a very fancy radio and it's got a lot of digital stuff that's going on in there. And yes, there are checksums, but that's at a little bit higher level. To understand how this works to start with, we'll concentrate on the analog side of things. Okay, so for technician license level, you're not going to learn everything about everything all at once. You're just going to learn a little bit called the basics. And then after you get your license, you can start learning as much as you want. And there's a lot of art and science. Okay, now we use the word add before in the transmitter when we're adding information. Another word that is the same meaning as adding information is called modulation. So that's one of the topics of our session here right now, modulation. So if we're adding information to a carrier wave or to a radio signal, that's called modulating. Usually the radio wave that we start with that we're adding stuff to is called a carrier. And we then modulate that carrier to create the wave. Now here's one of the simple ways of modulating the carrier. We can turn that carrier wave on and off. So we're either transmitting the carrier or we're not transmitting anything. That is called Morse code. And that was invented a long time ago. And that's how the Wild West got settled, was by sending Morse code all over, and how we got signals over to Europe when radio was first invented. And then there's talking, speech, and music. How do we get these things so that they modulate the carrier wave? And then there's data, of course, everything in higher levels of that. There's pictures, like television. And so there are a lot of different modulation techniques, and they have different ways of operating. They can change different properties of that wave in order to add the information or to modulate the wave. For example, there's a modulation technique that changes the amplitude. There's a modulation technique that changes the frequency. And there's a modulation technique that changes the phase of the carrier. We're going to focus on these first two for a little bit and see some actual differences between different types of this. Any questions here? Okay, first of all, I use the word phase, and we haven't talked about phase yet. So this is just a slide that talks about what phase means. if we have a sinusoid, a radio wave that is a pure sinusoid, then the different parts of that cycle are given the word phase. With any sine wave, we always associate the full length of the sine wave from the same part to the same part of the wave as being 360 degrees. If we break 360 into two, then we get the middle of the sine wave, that's 180 degrees. A quarter of the cycle is called 90 degrees, and a quarter is the other way is 270 degrees. So a full cycle is always 360, and a half is 180, and a quarter is 90. There's also the word phase that is used when you have two sine waves of the same frequency. Then we can talk about how far apart each one of those sine waves is from the other by talking about the phase difference between those two sine waves. And if you find the parts of the sine waves that are equal, then the number of degrees between those two same parts is what we call the phase difference. In this example, we see about a quarter of this sine wave right there, and that's where the beginning of the other sine wave is. So we say that these two sine waves are 90 degrees apart, or a quarter cycle apart. Here is another example of two different sine waves where now the phase difference between these two sine waves is 180 degrees. A little bit more complicated. Any questions about the word phase and what it means? Bruce?
I'm good.
Okay, I thought I saw you raise your hand.
Yeah.
Okay, so here is what Morse code looks like. And Morse code has an abbreviation called CW. That means continuous wave. And here we look at a very, very pure sine wave. And here we see that we have a switch called a key, which a telegraph operator likes to use in order to shut down the carrier or to let the carrier go. So this is an example where he keeps the key down for this period of time right here. He takes his hand off the key for a second. And here he has the key down for a longer time. And if we get the relative positions and the amount of times that the key is down correct, then we have a dot and a dash. And so if this was transmitted by the telegraph operator quickly, it would be the letter A. But we don't really need to learn the Morse code in order to get our license. Just remember, this is called continuous wave, and the same thing as Morse code, and it's the most simple modulation technique that there is. And that's because the carrier is either on, present, or it's not even there. There's nothing there. Next comes amplitude modulation. This is the early radios that we had when we were kids. When we listened to music on, I don't know, WKBW in Buffalo, New York, which is where I came from, we listened to 1520 kilohertz, and we called it an AM radio, amplitude modulation. Now this is a little bit trickier because we now start with the carrier. This is the thing that we, oops, gotta go back. This is the carrier wave. And here is an example of a tone. Let's say somebody's singing, and this is the frequency. It's a very low frequency that they're singing compared with the radio wave that we're going to modulate. So here's somebody singing, and this tone, actually, the value of this tone multiplies this carrier wave. And there's a little bit of a trick. You have to add one first, but we won't discuss that very much. And what we get is a radio wave that has cycles that are getting bigger in amplitude and smaller in amplitude. And there are many cycles like this. If a lady is singing a song, for example, and she's got this pure tone going for a few seconds, there will be hundreds of thousands and millions of carrier waves and cycles within that broadcast. But this is what the signal will actually look like. And this outside edge of the carrier wave is called the envelope. And the signal itself is called an amplitude modulated signal. And so you see, we have taken this audio tone at a low frequency and we have modulated the carrier to create the overall thing that is broadcast by the radio. Any questions?
So your receiver is tuned to that frequency and it delivers to your speaker the changes in the amplitude.
Yes, the receiver is going to take this particular signal with this carrier wave, and it's going to throw away all the other carrier waves that are in space that are at different frequencies. And then once it gets settled with this particular wave, it's going to eliminate the carrier and give back that tone. Thanks, Bruce.
Mhm.
Okay, composite signals. This process of adding information to that radio wave is going to create some signals. Now, this is a little bit more technical, and those signals are called sidebands. This is something that happens when you multiply two frequencies together. Two sine waves get multiplied together. You get some additional signals, and they're called sidebands. The sidebands and the carrier together represent what we just looked at on that previous slide. And they're together, they carry the information from the transmitter to your receiver. Okay, so this combination of carrier and sidebands creates what is called a composite signal. The word bandwidth now has something to do with frequencies. The carrier and the sidebands, they have different frequencies. And they occupy a slot in that spectrum. Remember that example we had where we had 4 radio signals and we showed 4 bumps on the curve? Okay, so that one of those bumps alone is what contains the carrier and the sidebands. Now, how far apart the highest frequency is in that bump on the spectrum is called the bandwidth. How far apart the highest frequency in that bump is from the lowest frequency in that bump is the bandwidth. So different types of modulation, and we're going to see a few more, they result in different signal bandwidths. Now here's the AM, amplitude modulated signal, when you have a pure tone. Let's say that some lady is singing a very pure tone and she keeps going on, and she never changes. That's just an example of what we can think of that causes this composite signal to have different frequencies as a result of that modulation technique that we just talked about. In particular, amplitude modulated signals, they still have the carrier frequency in there. So in this case, the carrier frequency was 800 kilohertz. That's right in the middle of the AM radio band that you could tune your radio to 800 kilohertz just by moving the dial. The actual tone is represented by the tone that the lady is singing is represented by a frequency content right here and another frequency content right here. This is called the upper sideband, and this is called the lower sideband, because this is a higher frequency than the carrier, and this is a lower frequency than the carrier. If we have a 600 hertz tone, that's what she's singing, 600 hertz tone, then our upper sideband will be at 800 plus 600 hertz, 800 kilohertz plus 600 hertz. That makes that frequency 800.6 kilohertz. And so now relating that new word that we just learned, bandwidth. Bandwidth is the highest frequency minus the lowest frequency. So if we have 800.6 minus 799.4, I think we get 1.2 kilohertz. So that would be the bandwidth of that lady's singing that pure tone. So this general statement here is kind of important. Amplitude modulated bandwidth is always twice the information bandwidth. The information, remember, is that lady's singing the 600 hertz tone. So the AM bandwidth is twice that, or 1200 hertz, which is the same as 1.2 kilohertz.
Ron, why is that? Why is that the case?
That is because if you take the mathematics of a sine wave and you multiply it by another sine wave with a different frequency, you get this result. Now that's a fairly complicated mathematical challenge, which we don't ask you to do, but we just believe that that happens.
Is it as simple as saying that whether the lower or the upper side, whatever, for instance, the voice, if it's 600 hertz, it's going to be 600 to the upside and 600 to the downside?
Yeah. For example, let me make it a lot more simpler by getting away from megahertz and getting away from these signals that are a long ways apart in frequency. For example, this carrier is, oops, got to get back. Oh, where did I go? The wrong way? Yeah. Okay, the carrier was at 800 kilohertz. That's a super high frequency compared to 600 hertz. So let me get away from that just for the sake of discussion. And I'll be a mathematician for a second, but I'm going to talk about a sine wave with 1 hertz and a sine wave with 4 hertz. Now, this is not radio. We're just talking about mathematics here. If I multiply the sine of f, the frequency, sine of 1t, that's what we do, sine of 1t times the sine of 4t, I'm going to end up with signals at 4 and signals at 3 and signals at 5. Now that's a mathematical thing that I can do in my head. And I don't really want you guys to do this, but
Excellent.
gentlemen,
Don't worry, we don't want to.
We won't, not a problem.
sine waves together. And mathematicians do this all the time. And of course, I did this all the time in all my schooling, and I did it 1,000 million times. So I'm very used to that, but we can go on. Does that partially answer your question, though?
Yeah, that's fine. Thank you.
Okay. I'm afraid that we lose a lot of folks right
Yeah, no, it wasn't important anyway.
It's going to be important because we're going to talk about changing the modulation technique in a second. Now, that lady is not going to sing her pure tone forever. In fact, the lady is probably singing in front of a band that has drums and violins and clarinets and saxophones. And so the sound that you hear when you hear music has lots and lots of frequencies, and it's not just a lady singing a pure sine wave. In fact, when I talk, I have more than one sine wave in my voice. I have many overtones and I have harmonics and things like that. So voices and music and sound in general has many frequencies all at the same time. And actually, sounds that make up voice are a very complicated mixture of multiple frequencies, anywhere from 300 to 3,000 hertz. Now, there's frequencies in music that are much higher than that, but amplitude modulation usually doesn't let that all pass. So they restrict the attention of the signals coming from the orchestra, for example, to the range between 300 and 3,000 hertz. It's not perfect fidelity, but we get music. You get voice. And so there are many different tones that are being modulated onto the same carrier at the same time. And those many different tones will then add to the frequency of the carrier. For example, we started at 300 hertz right here. We started with an example where we assumed that we're restricted to between 300 and 3,000 hertz. And so we're going to get a tone here, a frequency that's in that modulation of 800.3. That's 800 kilohertz plus 300 hertz, or 800.3 kilohertz. We're also going to get the highest frequency that's in that orchestra sound of 3,000 hertz, and 3,000 hertz is going to be added to 800 kilohertz, and we're going to get 803. Now there's a slight technical error on this slide. That last three should not be there, because we assumed that the 300 to 3,000 was our limits. So this is a mistake. Just think of this as being a 0 right there. And if you get over to the other side, think of this being 797 kilohertz. It is a mistake, and I can't correct the slide because I didn't make the slide. But all these extra sideband tones are being sent through the air at the same time as the carrier, as well as the lower sideband tones that present all the information and all the harmonics that are presented by musical instruments and by somebody's voice going up and down in amplitude and in frequency. The way I'm talking about, I can say high frequencies and I can say low frequencies, and the high frequencies are somewhere over here and the low frequencies are somewhere over here. And if we listen to Phil Sinnett talk, he's probably got frequencies that are even lower than this, because that's Phil for you. But we get two mirror image sets of sidebands that are created, and they're each 3,000 hertz wide. Remember that this is a mistake. It should be 0 right there, and this should say 797. So the bandwidth of this particular voice signal is 2 times 3,000 hertz, or 6,000 hertz. So the bandwidth of our strangely limited signal that we're going to process is 6,000 hertz, or 6 kilohertz. Okay, have we lost anybody? All right, let's move on from here. Now we're going to talk about a different way of modulating an AM signal. This is called SSB, or single sideband modulation. Now this is a real advantage. This was invented a long time ago, but it turns out that it is really much, much, much better than an AM radio band. So on that previous slide, the information that we had over here in the upper sideband was exactly the same information that we had over here in the lower sideband that was just on the other side of the carrier. In this case, we have a 600 kilohertz carrier, but notice that it's missing from the spectrum. What we do is we transmit only the upper sideband. That's why it's called single sideband modulation. Since the two sets of the voice sidebands carry the same duplicate information, we can improve efficiency a lot by transmitting only one sideband, and we don't even send the carrier. Then through the tricks of electronics, we reconstruct the missing carrier inside the receiver. And now, what is the bandwidth? The bandwidth, again, that same mistake as over here. Think of that as being a 0. The bandwidth is from here to here. And you could say it's only 2,700 hertz here, but let's just say that it's 3,000 hertz. And that is half of the bandwidth of the amplitude modulated version of the same music. Okay, now we're going to go down a different road.
Ron, can I ask one question?
Yeah, I'll go back to that slide.
Yeah, why is that efficiency important? Is it, can you put more stations and less in the
Well, if
more stations, or
we don't transmit the carrier, and if we don't transmit the lower sidebands, then we can put more power into the upper sidebands, and our signal can actually go further than if we sent the whole thing.
oh, got it. Okay.
We can put a lot more power into this and have the same power that we would have had in AM, but this power is focused.
Got it.
We're not wasting any power with this. We're not wasting any power with the other sideband.
Great, thank you.
Amplitude modulation is a long time ago invented, and it works. So that was the original goal of a lot of things, is just to make radio waves work. It's very easy to modulate an amplitude modulation type of modulation. This single sideband stuff is a lot trickier for the radio. Both the transmitter and the receiver have to jump through hoops in order to get this carrier back again so that it can extract the information from the electromagnetic spectrum. Okay, now we're going to go down that different road, and this is called FM. We're going to mostly about FM, frequency modulation. So instead of varying the size of the carrier, instead of varying the amplitude, if we use that information to vary the carrier's frequency, then we're using the modulation technique called frequency modulation, or FM. Now, FM bandwidth for voice on a ham radio is between 5 and 15 kilohertz. Now, we're going to try to put that number in the same thinking cap that we had some of our other numbers in. We had, first of all, let's review. We had 6 kilohertz for AM. We had 3 kilohertz for single sideband. And now we've got something between 5 and 15, and I usually think of that as being around 10 kilohertz for FM. So what are we going to do to create this? We're going to have this, here's the latest tone, this pure sine wave tone, and we're going to try to put that on top of this. But this time, instead of putting it on top, and so we can see the shape of that, what we're going to do is change the frequency. When this signal is high, we're going to have a higher frequency here. When the signal is low, we're going to have a lower frequency here. And then since this is a sine wave, this higher frequency will alternate with the lower frequency, and it'll alternate, keeping going, high frequency, low frequency, high frequency, low frequency. And that will be the method of modulation called frequency modulation. Notice that the carrier amplitude stays constant during the whole thing. So what happens if the guy sings louder? Let's say this tone here, this lady, whoever is singing, sings louder, then the sine wave would be bigger, wouldn't it? If the sine wave was bigger than this one, then this frequency would be even higher, and this frequency would be even lower. So that's how FM modulation works. It turns out that this is a better way of transmitting music over the commercial broadcast system, and we get much cleaner music when we use FM because it has a much higher bandwidth. Here is where we have to stay for a bit. Amplitude modulated voice, we already talked about that as having a typical bandwidth of 6 kilohertz. Now that's ham radio voice. If you're listening to your radio, the AM radio that you have in your living room, then that's a little bit higher. They allow 10 kilohertz of bandwidth for your broadcast type radio. But the ham radio is down around 6 kilohertz. Okay, the next entry in this little list right here is video. Now here's where the answer is 6 megahertz. Now that's a large bandwidth. And the way I like to remember this particular number in my own mind is that they used to say that a picture is worth 1,000 words, right? So if you think of the AM voice being the words, then the picture is 1,000 times that, and 1,000 times 6 kilohertz is 6 megahertz. So that's one way that I remember this number. Single sideband voice, that's that tricky technique that we talked about. The bandwidth of that is much less than AM voice. And think of it as being about half of the AM voice because we're throwing away the sideband on the bottom. Or we can throw away the sideband on the top. It doesn't make any difference. All you have to do is flip a switch on your radio and you can throw away the one or you can throw away the other one. Okay, let's look at single sideband digital. And you won't do this as a tech right away, but it's still available. And that's about the same as SSB voice. Instead of from 2 to 3 kilohertz, it could be as small as 500 hertz, or that same 3 kilohertz is right here. So just think of digital as being a little bit further on the lower side of the bandwidth scale. Now here's one of the more striking parts of this particular list. Here we're at CW. Remember that means continuous wave, which is also the same as Morse code. And there we are either transmitting the carrier or we're not transmitting the carrier. So the upper frequency and the lower frequency are extremely close together since there's only one frequency. So you can think of Morse code being very, very narrow bandwidth. In fact, the bandwidth of CW is very small, 150 hertz. Now remember how small that is compared to 6 kilohertz. This is 6,000 hertz, and here we're at 150 hertz. So that's extremely narrow for the bandwidth requirements for Morse code. If we go to FM voice on ham radio, okay, on ham radio, just ham radio, not your broadcast version, then I think of that as being 10 or 12 or 15 kilohertz. However, when you get to the broadcast band, if you turn on your FM radio in your living room and you listen to music, the bandwidth that they allow there is much higher than the band that we use, than the bandwidth that we are accustomed to on ham radio. it is much higher. Look how much higher it is. It's 10 times bigger than the voice bandwidth that we have on our ham radios. So some of these questions are some of the things that you might get on your license. So now we're going to see some of these questions. Here's that same radio band thing that we talked about before. And typically when you get that handheld radio in your hands for the first time and you're talking on the 2-meter band, you will use the technique called FM or frequency modulation. That's what we do most of all on the 2-meter band. When we get to 6 meters, you can do FM there, and you can also do single sideband. There are ways of doing single sideband on 2 meters, but we won't see them unless you get a very fancy radio. Now, when we get down here in these really low bands, if you ever get these real long antennas and the fancy radios and the amplifiers, then you're going to be using single sideband modulation most of the time. Okay, so that's a little bit of a summary. If I were you, I would focus on this corner up here when you're learning some of the stuff and maybe go over a little bit of some of these numbers here, but you don't have to remember all of them, not right at the beginning. After you get further into ham radio, then you start learning all these numbers and what you can do with it. Okay, so now we've got some questions on this. Are there any questions from you guys before we start on some of these license exam questions? Okay, let's move ahead. Why should you not set your transmit frequency to be exactly at the edge of an amateur band or a subband? Now, this question takes a little bit of thought. Obviously, if the FCC has let us transmit on certain frequencies that are totally contained in that color chart, then we don't want to transmit any frequencies that are outside that color chart. So with that in mind, what do you think the right answer is for this question? Now, this is a tricky one, so think a little bit more than just sending out that first thought.
It's D.
D as in dog.
Yes.
You're all right. Now, the most important answer in this, all of these are correct, is so that the sidebands don't extend outside the band edge, right? If we're going to transmit FM or AM, we're going to have sidebands, and we don't want to transmit those outside of the range that we're permitted to. But since we can have errors in our radios, or since our radio might not be perfectly stable, that's the reason that this answer is the best answer, and this is the one that they would grade you on. All those choices are correct.
But you are responsible for your radio.
Yeah, so you have to take care of this by moving your frequency to within the band instead of right at the edge of the band. Okay, what determines the amount of deviation of an FM as opposed to a phase? We're not going to talk about phase modulation. We're going to talk about FM. Try not to think about PM very much. Okay, what determines the amount of deviation of an FM signal? Now, I kind of went over this, but I didn't tell you that I was doing it when I did it. So what did I say?
It's A.
What is the answer?
A.
A.
Oh,
Charlie,
I would say B.
answer is C. Remember when I told you if the lady sings louder,
Okay.
then the frequency gets bigger. But the frequency that she's singing at is not going to be reflected. It's the amplitude of that signal that she's singing at that changes the frequency of the carrier to a higher level and a lower level in the peaks and valleys of her sine wave. Now, this is a tricky one, so
I don't get that one. I thought you said on FM what changed was the frequency and not the amplitude.
Yes, that is correct. The deviation, the word deviation here refers to how much the carrier has been changed in frequency. The amplitude of the carrier is never going to change. And so when you speak louder, you're going to get more frequency change in the carrier. If you're going to speak at a higher frequency, sing at a higher frequency, or sing at a lower frequency, that's going to change how far apart those high frequencies and low frequencies are in that picture. Now that you'll have to think about a little bit.
What does it mean by deviation in the question? I don't know what that refers to then.
Okay, I guess we should have defined the word deviation. That's the frequency changes within the signal. The frequency changes.
Well, if it has to change based on the carrier the modulating frequency and amplitude. Yeah,
Our amplitude of the lady singing, not how high, but how loud she sings, that increases the deviation. Now, if she sings a high note, a high frequency note, then that's going to make those compressions and those spacings closer together.
Isn't that a deviation of the FM signal?
In the FM signal. Let's go back. Let's see, it won't take too long. Let me see if I can go back. This is a hard one. It's one of the harder questions on the tech license. We're going to go all the way back to here. Okay, here's the lady's pure tone that she's singing.
Right.
Here's the lady's pure tone. And that results in the amplitude here is very large. It's at a positive amplitude. So that's going to increase the frequency in this area of the carrier.
Okay.
Here the amplitude is lower, so that's going to decrease the frequency in the carrier. You see that decrease exemplified by this wider apart sine wave down here.
Right.
Now, if we sing a much higher tone, if she hits a high note, if she hits high C when she's singing, instead of this frequency when she's singing, then this sine wave will have hills and valleys that are much closer together.
Right.
The hills and valleys would have to be closer together because it's a higher frequency.
Right.
That would make these compressions and expansions closer together in the carrier.
Right. So what about when she sings louder and softer?
When she sings louder, if she has a sine wave that goes up like the cursor, if she has a signal that goes up higher and down lower, that's louder.
Right.
Then that would make this frequency higher and this frequency lower.
Which is, how could you tell looking at it, which one was a amplitude change and which one was a frequency change? I mean, clearly the radio knows how.
If she sang that higher frequency tone, that wouldn't change the high frequencies here. That would just make the distance between the highs and the lows closer together. In other words, if she sang a tone that was twice this frequency, then we would have a compression here, an expansion here, a compression here, an expansion there, a compression here, an expansion there, and a compression here and an expansion there. But the actual frequencies in that expansion and compression would be the same. I gotta admit it's difficult.
It's tough.
If the,
So basically, what you're saying is positive going sine waves.
if
You're-
the time between peak changes, your frequency has changed.
The comment.
Go ahead, Phil.
Think about modulation in terms of what the modulating signal does. In AM modulation, the modulating signal amplitude changes the amplitude of the carrier, therefore AM. In FM, the amplitude of the modulation changes the frequency of the carrier, therefore FM. Now, in terms of looking at the FM carrier signal, that signal is being raised in frequency and lowered in frequency back and forth by the modulating signal because it's FM. The amount in frequency that FM signal changes is called the deviation. If the frequency, let's just say the carrier frequency goes up 10 kilohertz and it goes down 10 kilohertz. Well, it's being deviated 10 kilohertz. That's how much it's changing. And the deviation becomes important later on when you're trying to calculate the bandwidth required to transmit that thing. But just think of modulation in terms of what does the modulating signal do. If it changes the amplitude of the carrier, it's AM. If it changes the frequency of the carrier, it's FM. That's it.
Okay, thank you, Phil. Appreciate that very much. Let's go back to our questions here. Here's the hard one, and the answer is C. The amplitude increases. If we have a higher amplitude signal, it increases the amount of deviation of the electromagnetic wave. Okay, what happens when the deviation of an FM transmitter is increased?
So now that carrier, instead of going up 10 kilohertz and down 10 kilohertz, now it's going up 15 kilohertz and down 15 kilohertz. So what does that do to the overall carrier signal?
A
You're cheating. Anybody that's listening in on this, what answer do you want?
alpha.
Yeah, I heard you, Lee. A is right. It makes the bandwidth larger because the deviation is the difference between the highest frequency in the signal and the lowest frequency in the signal. And that is when she sings louder, then she gets more bandwidth. Okay. Which of the following is a form of amplitude modulation? Now, we've only talked about one of these here, so the rest of them you can throw away.
I say single side, I say C.
Single sideband, that is the right answer. What type of modulation is most commonly used for VHF packet radio? And don't worry about the word packet there. What did I tell you you'd be holding in your hand for the first time when you get your license? A handheld radio that is in the 2-meter band. And what kind of modulation are you going to use there?
Amplitude modulation.
AM is 2, right?
Charlie.
A.
A is the right answer. FM is what we use in the 2-meter band.
Yeah, okay.
Okay, which type of voice modulation is most often used for long distance or weak signal contacts on the VHF and UHF bands?
C, SSB.
C is the right answer.
So I would have
We're
guessed.
not going to do that too much on our handheld walkie-talkies, but that is the right answer.
Yeah.
You can get more power into the one band and get that information across longer distances if you throw away the carrier and you throw away one of the bands on the side. Okay, what type of modulation is most commonly used for VHF and UHF voice repeaters? Okay, we got a new word here, repeater. That's the very fancy radio that the club owns that allows you to talk on the 2 meter and the 440 centimeter band. So that word repeater is just a fancy word for a very fancy radio that the club works on.
Probably D.
It's still 2 meters. So D is the right answer.
D, right?
Okay, which of the following types of emission has the narrowest bandwidth? And now you should be able to answer this one right on.
C is in cat.
What?
C is in cat.
C as in cat. That is the right. It's the most, I'll go back one. It's the most narrow bandwidth that we have available in all of our list of modulation techniques. Okay, which sideband is normally used for 10 meter high frequency VHF and UHF single sideband communications? Now this is something that you have to learn. I want to give you the way that I learned the answer to this question. Now you can memorize the answer or you can learn it this way if you like what I'm going to tell you next. First of all, we have some bands that have very long wavelengths. Long wavelengths were on the left-hand side of that chart that we saw. The short wavelengths are on the right-hand side of the chart. Now the word lower sideband starts with a L. And the word long bandwidth starts with the L. That's how I remember that longer wavelengths use the lower sideband. If it's a higher frequency, then it uses the upper sideband because there's no L's in that. Now 10 meter happens to be close to the right-hand side. And so 10 meter is not long. Think of long as being 20 meters, 40 meters, 80 meters, and 160 meters, and all the ones in between. Those are really long. You have to have big antennas for those type of things. So what does that make the answer to this question?
A.
Okay.
That is the right answer.
We got it.
Okay, what's next? What is the primary advantage of single sideband over FM for voice transmissions?
I think it's D.
Is
I
D?
think it's C. It's C.
Okay, we definitely learned that SSB has a lot more narrow bandwidth than all the other ones except for CW.
It's Delta.
B happens to be correct. And A happens to be correct also.
So it's D.
They can't hear me.
Ah, no, C.
Narrower bandwidth.
Woo!
These two are not correct.
Okay.
Okay, what's the approximate bandwidth of a single sideband voice signal? Now, this is the one you should just be able to remember.
15, D.
B.
The answer is B.
3.
Okay, what's the approximate bandwidth of a VHF repeater FM phone signal? Well, to do this one, I would remember that AM is about 6 kilohertz. FM is more than that. Does that help you?
C?
C is the right answer.
Yeah, I remember the 10.
Just remember that voice for AM is 6 kilohertz. Remember that voice on FM is quite a little bit more than that. That should help you. Okay, what's the typical bandwidth of analog fast scan TV transmissions on the 70 centimeter band?
B.
I heard a
It'd be
B.
about 6 megahertz. Yeah.
I said a picture of
WCM.
1,000 words. So if you remember 6 kilohertz times 1,000, you get 6 megahertz.
Okay.
What's the approximate maximum bandwidth required to transmit a CW signal?
I'm sorry, B.
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 That's the right answer. That's the narrowest one of them all. And we have reached the end point for tonight's time. Now, we talked about some easy things and we talked about some complicated things and some stuff in the middle. And my explanation of FM and deviation is I tried to be accurate, but maybe if you listen to what I said over and over again, that might help. I'm not sure. But that's the most complicated thing we did tonight. Talking about Morse code was one of the easier ways of modulating a signal. So we talked about that, and you should be able to understand that by now. And then the definition of what an electromagnetic wave is. Even though we can't see electromagnetic waves, there's a lot going on. And it's a miracle that somehow when you interlock the magnetic field variations and the electric field variations, results in something that goes as fast as the speed of light. So that's quite an interesting physical phenomenon that we talked about a little bit. By the way, that diagram that I showed that had the two different color grays, the stripes and the gray, the electric field was the vertical one. And that kind of an electromagnetic wave is created by an antenna that is mounted vertically because the electric field comes right off in the same direction as the antenna is. If we had a horizontally oriented antenna, then the electric field would be horizontal and the magnetic field would be vertical. But they are always locked together 90 degrees from each other. And that's like I think of it as being one of the really interesting phenomenon in physics. Okay, are there any more questions from anybody on anything? And we can go back to some of these issues if you like.
Good. I'm good. You good?
I'm good.
We're good on our end.
Okay, well, Mark, you can take it from here then. I'll be available, and if you would like to ask me any questions, please know that my name is Ron Laspiza, and you can reach me at an email address that is almost the same as my name, rlaspisa@cox.net. RLASPISA@cox.net will work. And I'd be glad to answer any questions that you have anytime, today, tomorrow, next week, at any time.
Thanks, Ron.
Okay,
Thanks
you
for everything.
for your time and your attention to some of these interesting things.
Ron, I agree. Thank you. I agree with them. Thank you very much. I just
Great
want to,
job, Ron.
Oh, thanks. Everything. Bye.
So guys, how are you feeling about this?
I'm gonna go back and do some homework.
More reading again.
Do what?
Need to do it, read again, read more.
You know, the Buck book doesn't cover it in this fashion, so it's a different way of illuminating it.
Yeah, yeah. And
The good-
whichever way
the
you
good
look
news
at it,
is-
you know, the main thing is when you start learning, you know, the theory behind the question, that it makes the questions a lot easier to answer.
Yeah.
Yeah.
It's really not all a bunch of, you know, smoke and mirrors and everything like that, even though I kid about that. You know, it's a case that it's very straightforward. It's been around since Marconi.
Or let me add that you could just memorize the answers to all these questions. And
Well,
then
that's true
learn the
too.
reasoning behind the questions and the answers later if you want to do it. A lot of people do it that way, and it's okay. They don't care whether you understand everything perfectly when you answer these questions. Multiple choice. So you answer the question, you get it right, you get it wrong. And that's it. Go on from there.
And there are lots of people that have done just that. They learn the test, they memorize the test, they pass it, they get their license. Some people don't care about learning the theory behind anything. They just, you know, want to use it and talk on the radio, and that's cool. But, you know, just like I've told the group here, one of the things that you have to look for is if things go south and you're, you know, with your wits and a few pieces of wire and other things like that, it's kind of nice to know the, you know, just like Ron introduced tonight, the 300 in lambda can give you your frequency. It can also help you figure out antenna lengths, things like that. So there's some very useful math in all this that are easy, you know, math. It's not, you know, it is not digital calculus or something. Yeah, you can get into that. But the main thing is a few basic equations will get you out of just about any jam, you know, you could get into, especially if you don't have everything in the world to work with.
Can I plug something?
Absolutely.
In the chat window, I put a link back. It's probably half hour back now. Over the years, when we've done this class and other classes, questions come up a bunch, and I've collected some of those and provided answers for them on the SCARS website. If you look in the chat window, you'll see a link there that ends with cultural enrichment. And if you click on that, there's a whole bunch of stuff related to what we talked about, what Ron talked about tonight, and what he's going to talk about, and others will talk about in coming weeks. So take a look at that. There may be some stuff there that'll help you learn some of this stuff.
Thank you.
Okay, I just put my email on. Get there.
I think that was
Breaking up. You put your email address in there, Ron?
Just now.
Okay.
I think the big thing to do is make sure you look online. Following Ron's discussion, I've updated his 2 errors, or the 3 errors that were on that slide that the
How did you
lead
do
had.
that?
Re-edited the graphics, man. Magic.
FM.
But I didn't do it this time.
I have done those. So if you wish to download a set of those slides, they are there now with the changes made, and
Okay.
the bandwidth, the band tables have been adjusted slightly since the one that he showed on the screen, and I've put the new ones in that slide deck. So if you go on the website, you'll get the current stuff. And remember, last time we said that the band plan, the piece that's the big eye chart that Ron had, is on the week 2 website, so you can download those. And
Yeah,
print those out.
I put a link there in the chat window for that as well, because the one in the slide set doesn't have 630 and 2200 meter bands in it.
Yeah, it's on the webpage. It
is? Okay, very good.
Yeah, but you guys won't be there for a while, so don't worry.
And I don't think there's any questions for those, so it's not. But I did update those slides in the Ron's presentation as well. So we're ready to go. Any
And
other
guys,
questions?
one of the biggest things that you can do for yourself is the w5nor.org website has got so much information